All right, chemistry students, welcome. This is video 6.1. We are beginning to introduce chemical bonding, and there are a few things we want to talk about. To begin, we want to look at chemical bonds, the different types of chemical bonds, the ionic bonding, covalent bonding, and also a little bit about metallic bonding. So first and foremost, we want to know what a bond is. Well, if you take a look here, we have this diagram. It's basically describing to us how a bond can occur and why it occurs. Basically, electrons, they are attracted to the nucleus here of the atom. This attraction causes different atoms to come together to form a bond. Now, this attraction here is what the chemical bond is, and it is basically representing one bond. There is an exception, however. It is not always 100% transferred or shared, and we're going to come back to this here in a few slides. So the textbook definition here of what a chemical bond is, you can write this down. You have the force of attraction that holds two atoms together. Now, for objective 2, you're supposed to look at why is that the case? Well, you can see here that this is a diagram of potential energy. And when a bond forms, the potential energy is going to actually drop. This provides more stability for a compound to form, and that is what or why a chemical bond actually forms. Now let's look at a few different types of chemical bonds. First of all, this chapter is really dealing with nonpolar and polar covalent bonds involving molecular compounds. So I want to talk a little bit about what that is. We have here a picture of a nonpolar covalent bond. And nonpolar covalent bonds means the electron is shared equally. So this atom and this atom are equally sharing the electron. Down here, however, you can see one cloud is a little bigger than the other. In this case, that is a polar covalent bond. And that means the electrons are not equally shared. So to kind of help you remember this, between what is a nonpolar and polar, think polar, North Pole, South Pole. We're at the different poles of the Earth. So the electrons are either way far away from the center or close to the center. In a nonpolar covalent bond, they're more in the center. They're more equally shared near the equator. Polar, think of the poles, the electrons are far to one end, far to the other. This picture also here does a very good job of showing a polar covalent bond. One gentleman is going to have more of the money than the other gentleman. A diagram here, or a little animation that shows a covalent bond here forming between a molecular compound. Now, a molecular compound, you're going to see this here written sometimes in a few different ways, but really with a molecular compound, you get a few different things that can form. With a molecular compound, you can get a few different things that can form. So really, a molecular compound, you're going to need to know this here. A molecular compound is a compound that forms between two non-metals. All right? So make sure we know that. So down here in our example, we have a covalent compound. Basically, this is a non-metal and a non-metal here, where we have sharing of electrons. All right? Oh, spelled that wrong. No E in there. Sharing of electrons. That is a covalent bond. And again, there's two types of covalent bonds. There is nonpolar covalent and polar covalent, all right? And they're sharing electrons either at the poles or more so in the middle, all right? Now, let's move on here and take a look at ionic bonding. Ionic bonding here, we have a gentleman who has all of the money and a gentleman who has hardly any of the money. So in this case, we can say ionic compounds completely transfer the electrons. They're completely transferred and there is no sharing of the electrons. Here's a diagram. This usually occurs between a metal and a non-metal. Now, here you can see you have a metal sodium, all right, that's our metal, and our non-metal chlorine. And we end up here with sodium chloride. Sodium has 1 electron to give up. Chlorine has 7 in its valence shell. If you think about chlorine's electron configuration, it's going to end here in 2s2, 2p5. So its outermost energy level here has 7 electrons. And really what's going to happen, if you think about our trends for chapter 5, electronegativity increases going across and decreases going down a period. Chlorine, which is over here on the periodic table, it really wants an electron. So it's going to take one of sodium's, if you think of Na, it's over here on the periodic table. So chlorine is going to take one of sodium's electrons, and that makes it an ionic bond. As far as, whoops, we don't want that up right now. As far as metallic bonds go, here we can see metallic bonds form a sea of electrons. Each one of these atoms has multiple electrons. And these electrons are easily able to flow in and amongst all over all of these different metals. And a metallic bond, of course, they're going to be involving metals, and most of the time they're going to be dealing with our transition metals that we learned about. All right, so transition metals is most of the time a lot of the metallic bonding occurs there within those sea of electrons. Now, one last thing that we need to cover here is how to basically look at electronegativity difference in classifying bonds. Now remember, electronegativity is how bad does an atom want an electron, all right? That is kind of our definition there for electronegativity. How bad does an atom want an electron? Well, we have this scale, and this scale goes from 3.3 down to 0, and there are different levels, and it's going to be important for you to basically know this scale, okay? And kind of to make it a little easier on you, what I went ahead and did was we put this together here, which this is a kind of, if you look at it, a line graph of how the ionic polar covalent, which is equal sharing, and nonpolar covalent is equal sharing, and polar covalent is equal sharing of electrons, and how those fit together. So if we take a look here, 1.7 is our magic number. That's the difference between a covalent and an ionic bond. You need to know that. So right here you have our trends. Nonpolar covalent, equal sharing of electrons from 0 to 0.3. You need to memorize this trend or these numbers. Polar covalent, so again, the electron is at the poles. It's at the far ends away from the middle sharing point for the electrons. That is going to be greater than 0.3 to 1.7. All right. And as far as ionic, that is 1.7 to 3.3. So if in here, if you want to write in, this is greater than 0.3 and greater than 1.7. So if it's 1.7, it's polar covalent, okay? If it's 1.7, it's polar covalent. If it's 0.3, it's going to be nonpolar covalent. And what we can do, where these values come from, these numbers, is on your periodic table, you actually have a periodic table of electronegativities, and on the bottom of it you have the electronegativity value, which is how bad it wants the electron. Fluorine here is the highest. It is 4. It is configuration 2s2, 2p, 5. It wants one more electron to become a noble gas right over here at group 18. So it really wants an electron. Down here, francium is the smallest at 0.7. It doesn't really care about its little s electron that it has. It'll knock that off and lose it. That's not a big deal. So again, the trend is increasing across and decreasing down for electronegativities. And we apply that here in one of our example problems. So let's take a look here at our example problem. All right. Again, we have our trends here that we're going to need to use. And let's take a look here at our example problem. Again, we need to remember 0 to 0.3, 1.7 to 3.3. Now, the electronegativity of sulfur is 2.5. Find the difference in electronegativity between sulfur and hydrogen. So if we say hydrogen and sulfur are bonded together, and sulfur here is a 2.5, and it gives you hydrogen, and again, you could get this from the periodic table of electronegativities, but you're given them. All you're going to do is find the difference. So 2.5 minus 2.1 gives you a difference of 0.4. Does that make it nonpolar or polar covalent? It is polar. There's your answer for hydrogen and sulfur. Now, what if we compare sulfur and cesium? So sulfur and cesium. Again, cesium is going to be a 0.7. Sulfur is 2.5. We're going to subtract the difference here, and we're going to end up with that as a difference. Type it in your calculator or figure out in your head of 1.8. Again, that falls here more into the ionic section. So it's a difference of 1.8, and it becomes an ionic bond. And then last but not least here, we want to do sulfur and chlorine. Again, sulfur is has an electronegativity of 2.5. It kind of wants electrons pretty bad. Chlorine has electronegativity of 3. It really wants electrons. If they were to bond together, we would get a negative 0.5. We're just looking for the difference here. The negative really doesn't matter. So a 0.5, if we look back up here, 0.5 puts us in the polar covalent range. So we could label that polar covalent. That is it for our Chapter 6.1 video.